Okay, so we've talked about this simple linear regression model, just a line. And then we talked about how our goal in fitting this model is going to be to search over all possible lines and find the line that minimizes the residual sum of squares. We haven't talked about how we're going to do that. That's going to come next. We're going to talk about specific algorithms for searching over all possible lines to minimize residual sum of squares. But right now, let's just assume that we have some fitted line, and let's talk about how we're going to use it and how we can interpret the parameters. Let's start by contrasting the model from the fitted line. So our model, which I've written again here, is in terms of parameters. These are parameters. They're unknown variables of our model. And our goal is to estimate these parameters, fix values of these variables based on our data. And so that's what W hat represents. These are our estimated parameters. And these take actual values. So for example, maybe our intercept is minus 44,850, and our slope is 280.76. And these aren't random numbers that I generated here. This comes from the first course. If you look at the notebook for doing the regression fit of sales price on square feet, these were the numbers that came out for these two parameters. Okay, so these estimated parameters define a specific line. Okay, that's what this is. This line represents minus 44,850 plus 280.76 times x. So a model is in terms of some parameters, and a fitted line is a specific example within that model class. So it's a specific line. Now let's talk about how we can think about using our fitted line. So one thing that we can ask is to predict the value of this house that we'd like to list for sale. So this house has some number of square feet, and we'd like to guess the price. And how are we going to guess the price? Well, it's very straightforward. We're just going to plug into our fitted line. And so we're going to take the square feet of this house, which is represented here, plug that into the equation of this line, and that's going to produce our estimated value of the house right here. I want to mention one more thing here. So I want to mention that y hat, that's our predicted value of the house. Y hat is exactly equal to f hat of x. Okay, our model, remember our model said that yi is approximately equal to f of xi. But when we go to do a prediction, y hat, that's exactly equal to f hat of x. And why is that? That's because the error is equally likely to be above or below the line. And f hat represents our best guess of the line given our data. And so if we want to guess the value of the house, we're unsure if that error for that specific house was above or below the line. So our best guess is to put it exactly on the line. Well, I can use this fitted line also if I'm a buyer, not just if I'm a seller interested in listing my house for sale. So for example, what I mean here is that I might have some amount of money that I can spend on a house, and I want to know how big of a house can I expect to purchase with that amount of money. Well, instead of estimating or predicting the value of the house, I can think of predicting the square feet. So just using this equation in reverse. So I have some amount of money in the bank, and that's going to be dollars in bank is this. And then I'm going to look at how many square feet I believe that I can purchase with that amount of money. Okay, so let's just go through a concrete example. Here's the fitted regression line I talked about before. So it's minus 44,850 plus 280.76 times x. And what I'd like to do is predict the value of a house that has 2,640 square feet. So what I do is just plug in 2,640 into this equation. That's my y hat. And that comes out to be, if you do that calculation, $696,356. Likewise, I can say, well, I want to predict how many square feet of house I can purchase if I have $859,000 to spend on the house. So if you do this calculation, you get that you can afford a house, or you expect to buy a house that's roughly 3,219 square feet.